we will study BV classical master equation, examples, and application. Let me briefly remind you what BV equations were. We considered a manifold that is a T star of 1, x. And now let me write everything in terms that physicists are using. Physicists are using phi I as coordinates on x and phi I star as coordinates on the fiber. Parity of phi I star plus parity of phi I is 1 moduli 2. BV classical master equation is ds over d phi I ds over d phi star I.
I'm sorry to interrupt, but it seems like your battery is running low. You might want to connect it to something.
Oh, thank you. It was another problem that I had, but I already solved it. Thank you very much. While I was fixing one problem, I hope it's better now. So this is classical master equation. So why do we need this classical master equation? We need this classical master equation because there is a general theory that if you have S solution to classical master equation on x times y, actually, I'm using t star of 1. And if you have L, that is Lagrangian submanifold in t star 1 of x, then integral over this Lagrangian submanifold with some measure, I am not talking about this measure, gives object that looks as follows. E to the 1 over h bar S induced, I'll put it like this, plus O of h terms, and S induced being a function on t star 1 of y also solves classical master equation. So it is a very powerful principle, and we will see many examples of it. But let us start with understanding what could be solution to classical master equation. Let us consider the simplest case, S of phi star, that is just a function of phi. It is clearly a solution. Now, take a vector field, Vi of phi, such that Vi of phi d over d phi I applied to f of phi equals to 0. This could be expressed in terms of phi star Vi of phi f of phi, and here we have this BV bracket equals to 0. So BV bracket, so I will define it on even quantities. I will call them G. It's defined as for even G1 and G2. So in this way, I may say the following. Consider formal odd parameter C. Odd. Then invariance of function f with respect to a vector field V could be expressed as follows. We would say that S that equals to f of phi plus C phi star I solves classical master equation. Now let us try to generalize this condition of symmetry. There is the following interesting generalization. Let us try to look at this generalization. So here we have our original stuff. And here there is an extra stuff. Here conditions are VA, VB, Lie bracket is FABC, ABE, VE, and of course FABE are structure constants of the Lie algebra. So it is kind of a deep generalization. Let me discuss how the computation works. Here we compute classical master equation on the space that is T star shifted by 1 to X times Lie algebra shifted by 1. Here CAs are coordinates. Oh, I'm sorry, on the Lie algebra G shifted by 1 in parity. Now it is instructive to see how computation goes. Consider alpha, easy case. X is the point. V equals to 0. We have just this. This object is known as a Chevalier-Eilenberg differential, rediscovered later as BRST differential in physics. So what happens if let me call it SE, Chevalier-Eilenberg. I have F, C, C, C star. And then I consider all pairings between C star and C. And what I'll get? I'll get something quadratic in F, linear in C, linear in C star, and cubic in C. And this is nothing but Jacobi identity. I can write it with the indices. We will get here F, A, B, E, F. Okay, A, B, C, F, A, D, E, CB, CC, CD, C star E. And this is Jacobi since C's are anti-commuting. Okay. So this was an easy case. Now let us add to this easy case that is easy prime, where we have this. So here I just put function to be 0. Easy prime is just almost the general case. Now, what should we compute in taking classical master equation? The new phenomena would be contraction in the BV bracket between phi star and phi. So symbolically, I have C, V of phi star plus 1/2 F C star. And the same thing. Now I will look for terms quadratic proportional to C squared. How can I get these terms? One way to get these terms is to consider pairing between these two guys. So phi star would be paired with phi. And this term would be CA-CB, VA-VB Lie bracket with the power I, phi I star. But there is also another way to get terms that are proportional to C squared. They are coming from pairing between this term and this term. We take C star out of this and pair it with C out of this. So we will get up to the sign and coefficient F, A, B, C, C, A, C, B. Okay, I write here plus minus. I'm showing the idea. VC I, phi I star. So for these terms to cancel, F should be structure constant of the vector fields that produce a symmetry. And now it's very easy to consider the general case. And here we obtain the following statement. System with symmetry may be reformulated as a solution to classical master equation. But actually, classical master equation is more involved subject, generalized concept of systems with symmetry.
Excuse me. This symmetry,
Yes, please.
global physical symmetry or gauge redundancies.
Yes. So V is a physical symmetry. V is a vector field. We should try to understand. So please interrupt me. Maybe I go too fast today. We would like to understand this later on as a classical action of matter fields. Okay, no, when it is not zero, of course. So let me go up here. This would be classical action later on. This would be symmetries because LVF equals to 0. And this would be algebra of symmetry. Okay? I don't want to rush.
BRST is about gauge invariance, right? I'm still a bit confused.
Okay, so what I'm trying to explain here is something that is deeper than BRST. We will come to BRST as a particular case later on. You see, in order to avoid your confusion, I am already able to explain to you in short terms right now what BRST would be. Okay? I don't want you to be confused. 1 second. I just want to take this formula out. Okay. I want to tell you right now what BRST would be. Okay? BRST that you know would mean that we take exactly this BV action. I call it BV action. And is restricted to a very special Lagrange submanifold. How do we define this Lagrange submanifold? We define this Lagrange submanifold by demanding that some functions that I'll call E alpha of phi equal to 0. So here is a picture. If I impose some condition on E alpha of phi, this space E alpha of phi star is no longer a Lagrange submanifold. It has dimension less than 1/2 of dimension of the space of fields phi and phi star. But it is possible to construct so-called conormal bundle. And it is done as follows. We may take objects that are phi I star to be the following. B alpha di E alpha of phi. So now there is a claim. This is also a Lagrangian submanifold. Proof. Let us consider symplectic form on this space. So you may see, so I'm not going to make this computation right now. So we will compute it later. When it will be time to study it. And then f of phi, and then we consider f of phi plus c v phi star plus c star f 1/2 would be reduced, would be restricted to a submanifold that I described above. And we will get f of phi plus. It's interesting to see what we will get here. LV of E, and here we will have B alpha VACA. And here I will get a restriction to the equation that E alpha equals to 0. And I will also imply condition that C star equals to 0. And this is called gauged fixed action. And these are called BC ghosts. So this is briefly how ghosts appear in this language. So unfortunately, I have not seen who asked me this question. Probably I need to switch the screen. But this is briefly, I will put it briefly, what VRST is from BV perspective.
So do you mean the symmetry here on this page include gauge redundancies.
Yes.
So,
Yes.
so gauge case is just a special case.
Yes. So my main message is that BV language is a universal language, but it is much more general than a particular gauge symmetry. You may consider it for gauge symmetry, you may consider it for external symmetry.
Like flavors and
Yes, yes. So if you wish, like flavor symmetry or like supersymmetry. Like flavor, like supersymmetry.
I mean, like Poincaré symmetry. Is that
yes, like Poincaré symmetry. However, for Poincaré symmetry, it's not that interesting. It's much more interesting for supersymmetry. And we will come to this example later. But at the moment, you see, I want to show you the formula. I mean this formula that corresponds to classical symmetry, to classical treatment of symmetry. And if you integrate over C, it means that you consider symmetry as a gauge symmetry. If you consider C as an external parameter, you consider it as an external symmetry. So it is a universal formula. And moreover, it's not the most general formula. So here I just try to show you how standard construction with ghosts comes out. So since you will have questions, so whenever you have questions, I'm trying to answer. It's my goal. So now let us have a 10 minutes break, and then we will continue with generalizations and applications and example. Okay? So I will try to continue. Solutions to classical master equation generalize the concept of symmetry in several ways. We will consider the following way. Suppose we have f of phi plus, and now look what I'm trying to put here. CA, CB, PAB, IJ, phi I star, phi j star, plus 1/2 FABE, CA, CB, C star E. I added new term, and the only condition that I will demand is that this S solves classical master equation. In this case, there would be modifications of equations. Of course, there will be equation LV A of F equals to 0. However, and this comes from terms linear in C. However, from terms quadratic in C, we would have LVA, sorry, I will write it differently, VA, VB, I, so it's a Lie bracket, would be equal to FABC, VC, I, plus an interesting term, PAB, IJ, DF over D phi j. New term from terms quadratic in C. I will get it from contraction of this type. Phi star from this pi term interacts with this F. And this is a new concept. It is called on-shell action of a symmetry. So what do we mean when we say on-shell? We understand S of phi as action in classical field theory. That's why df over d phi j equals of 0 are classical equations of motion. And we see that algebra is represented moduli ideal generated by classical equation of motion. That's what is written here. Now, let us see where we have such phenomena. Maybe I just dreamed about this condition. However, I can give you an example from ordinary geometry. Suppose x is SON. Sorry, S is X is Rn. G is SON. Then I can realize the BV action as phi 1 square plus etc. plus phi n k square. It's better to put indices up. The vector fields vi of phi are some matrices Tij, A. They are linear in phi's. So A here goes from 1 to n minus 1 over 2. Now I will do the following trick. I will integrate E over S BV over the very special Lagrangian submanifold. I'm sorry. I'm sorry. I will consider, I'm sorry, I will consider a BV integral. In the following settings. I take x1 to be R. I take x2 to be R n minus 1 times G shifted by 1. So I can construct SBV So I will construct SBV in the standard way. Is a function on T star shifted by 1 to R times T star shifted by 1 to R n minus 1 times T star G1. And then I will integrate over a Lagrangian submanifold here, given by equation phi 1 arbitrary, phi 1 star equal to 0. After the integration, I will get S induced on that solves classical master equation. the integral would be Gaussian. And could be easily taken. So now let us see the formulas. Plus so I would not take care about this term. I would not take care about this term. What bothers me is phi 1 that sits here and phi 1 that sits here. So interesting piece would be CA, TA, I1, phi 1, phi I star. So when I will take a Gaussian integral, these two terms would produce CA, TA, I1, phi I star, CB, TB, I1, here index is J. Yes, it is a desired term. Desired, anticipated. And it leads to the concept of BV invariance or on shell. Invariance of the action I hope I can write it phi 2 square plus phi n square plus sum over ij not equal to 1. CA, CA, ij, phi j, phi I star. Plus CA, CB, okay. You may think that this is just mathematics and it is not related to physics. However, this is a prototype of how supersymmetry is realized. Okay. This phenomena happens in supersymmetry that we studied. Remember, we studied n equals 1 and n equals 2 theories. Consider a dimensional reduction of to dimension 0 here where all fields do not depend on time. Still, we had an action there. That had the following form. We had a superfield plus we had an F squared term. So let us try to treat it from the point of view consider it from the BV point of view. So first of all, we had a field phi, and then there were two supersymmetries. So let me remind you that Q was d over d theta plus theta d over dt, and Q bar was d over d theta bar plus theta d over dt. Now we study fields that do not depend on t. So now Q is just this, and Q bar is just this. We decompose superfield phi as phi plus theta psi plus theta bar psi bar plus theta theta bar f. So the action S was W prime of phi f, let me call it S1, plus W2 prime of phi psi psi bar. Okay. Now, how did we got this f squared term? From what we called d bar phi, d phi. But now d is again d over d phi, d theta, and d bar is d over d theta. And here we have d2 theta. So, so the only term that we have here is f squared. So it is because, say, d phi is psi plus theta bar f. Similarly, d bar phi is psi bar plus theta f. And in order to get to theta, we need to extract f terms. Okay, good. So we have this, what is called matter action in the form f squared plus w prime f plus w2 prime phi psi bar. Now, we may integrate out f field like we integrated out phi 1 field in the previous example. And we will get supersymmetry realized on shell. Actually, how does it happen? Say we have Q and it is. So corresponding vector is phi star psi. And here we put epsilon. So epsilon is a ghost for supersymmetry transformation. But Q not only takes phi into psi, it takes psi bar into f. So here we have epsilon psi bar star f. So interestingly enough, when we will integrate f terms out, we will have exactly the same phenomena that we observed in the case of system with rotation. And this is how on shell. So this is a toy model So when we integrate FR, this is a toy model showing how on-shell realization of supersymmetry happens in real physical theory. When you integrate this field out, you will get W prime of phi plus epsilon psi bar star squared. And here you will have W prime bar squared plus W2 prime phi psi bar. Plus epsilon psi phi bar plus epsilon psi bar star W prime of phi. So there is something like 1/2, but I don't care about it. Plus interesting term. Shows that supersymmetry is realized on shell. Okay, so that's what I wanted to tell you today. And now questions.
Or maybe I have a question about the notation.
Yes.
So G is the Lie algebra.
Yes.
Right. So when you write the shifted T star G, well, what does it mean?
It means, so shifted means that I consider Lie algebra with opposite parity. It means that functions, it means that I consider coordinates on the they consider linear coordinates on Lie algebra as odd variables.
Well, what is T's cotangent bundle of?
Okay, so let me come back. Okay, so then you ask. Okay, so I'll take a blue pen. So here. So where is cotangent bundle to Lie algebra? It is here. It is C star. Coordinates on T star of 1, shift of Lie algebra of 1. But this is isomorphic to G dual. So probably I went too fast.
And this equation s equals for phi plus something. There's a generalization. Can you show the formula of the generalized? You have added a
Yes.
new term.
Yes. 1 second. Yes.
Oh yes.
Here is the
this-
formula of the new term.
Yes. I'm wondering if this has anything to do with an anomaly in quantum mechanics. The pi ABIJ.
No, it's not about anomaly.
Okay.
It is about so-called on-shell closure. So using this term, we may say exactly how symmetry commute. So in the classical case, I don't mean classical versus quantum, I mean in conventional case. Symmetries were forming Lie algebra, and they were independent on the system on which they were acting. And here, in this equation, we have a new phenomena. Commutator of symmetries depends on f that is invariant. So equation exclamation mark mixes together invariance and symmetries. So that's why it's kind of a new phenomena, I would say, in mathematics.
F is
People used to say, go on.
F is the classical action. Is that right?
Yes.
But sometimes for some symmetries, it's I would call it action density. I mean the action the function the Lagrangian times the volume form is invariant, but the Lagrangian the function is not itself is not invariant. For example, in GR and relativistic particle. In the action, the dt also has a factor beta under the Lorentz transformation. For example,
So I consider f as a generalization of the action, not as a generalization of a Lagrangian.
Oh, okay.